In this video, let us demystify Markov chains. Financial time series such as daily prices of a stock index or the exchange rate between two currencies exhibit complex and seemingly erratic behavior. Unlike deterministic systems governed by the predictable physical laws, financial markets are driven by a confluence of factors including economic news, corporate performances, geopolitical events, and crucially human psychology. This results in data characterized by inherent randomness and uncertainty. A key feature of financial returns is a phenomenon known as volatility clustering, where periods of high price fluctuations tend to be followed by more high volatility periods, and tranquil periods are followed by more tranquility. This dynamic behavior, where the variance of returns is not constant over time, defies the simple linear modeling. Furthermore, asset prices often follow a random walk, where the next price movement is largely unpredictable based on the past movements, making forecasting a formidable challenge. These characteristics necessitate a modeling framework that can explicitly account for randomness and evolving statistical properties. Deterministic models are inadequate for this task. Instead, the language of probability and stochastic process is required. A stochastic process is a mathematical construct used to model systems that evolve over time in a probabilistic manner. Formally, it is the collection of random variables xt indexed by the set t, which typically represents time. Each random variable xt describes the state of the system at a specific time. This framework allows for the description of not just a single random outcome, but an entire trajectory of outcomes unfolding through time. For example, the daily closing price of S&P 500 index can be modeled as a stochastic process where xt is the random variable representing the price on day t. The actual sequence of prices observed over the past year is just one realization or sample path of the underlying process. This perspective is powerful because it allows for quantification of uncertainty about future paths rather than attempting to predict a single deterministic future. Within the vast universe of stochastic processes, the Markov chain holds a special place, particularly in economics and finance, where it is considered a workhorse model. A Markov chain is a specific type of stochastic process that simplifies the complex web of dependencies inherent in time series. It does so through a powerful and elegant assumption about the system's memory. Instead of assuming that the future state of a system depends on its entire potentially infinite history, a Markov chain posits that the future is conditionally independent of the past, given the present state. This simplification, known as a Markov property, transforms an often intractable modeling problem into a manageable one. It provides a structured way to analyze systems where the immediate past contains the most salient information for predicting the immediate future, a characteristic often observed in the financial market dynamics. The defining characteristic of a Markov process is the Markov property, often described as memoryless. This property states that the conditional probability distribution of future states of the process depends solely on its present value or present state, not on the sequence of events that predicted it. Informally, this is captured by the maxim what happens next depends only on the state of affairs now. Mathematically, for a sequence of random variables x0, x1, x2, so on, the process satisfies the Markov property if and only if for any time step n greater than or equal to 0 and any possible states I, j, I naught, and so on I n minus 1. P of xn plus 1 is equals to j such that xn is equals to I, xn minus 1 is equals to in minus 1, and so on x0 is equals to I0 is equal to P of xn plus 1 is equals to j such that xn is equals to I. This equation formally asserts that given the present state xn is equals to I, any information about the past states is irrelevant for predicting the next state. The power of this assumption lies in its ability to dramatically reduce the complexity of a model. However, its application in finance is not without a nuance. While the weak form efficient market hypothesis suggests that the past price information cannot be used to predict the future prices, many well-documented market phenomena, such as momentum, suggest that market do possess some form of memory. Therefore, applying a Markov model is not a declaration that markets are truly memoryless. Instead, it is a pragmatic approximation that assumes that most recent states, for instance, the current market volatility regime, contains the most critical information for predicting the next immediate state. A discrete time Markov chain is a Markov process with a discrete index set. A discrete time Markov chain is a Markov process with a discrete index set, and typically a discrete state space. It is defined by two key components. The first one is its state space. This is the set of all possible values or conditions the system can occupy. The state space must be countable, meaning it can be finite or countably infinite. For our purposes, we will focus on finite state spaces. The next component is the transition probabilities. These are the probabilities of the chain moving from a state I to a state j in a single step. This is denoted as pj, which is equal to probability of xn plus 1 is equal to j such that probability of xn is equals to I. These probabilities are assumed to be constant over time for a time homogeneous Markov chain, which is a common and powerful simplification. The dynamics of a discrete time Markov chain are completely specified by its transition matrix P. This is a square matrix where the entry in the ith row and jth column is one step transition probability Pij. This is how the matrix looks. This matrix has two fundamental properties that makes it a stochastic matrix. All entries must be non-negative. That is, Pij should be greater than or equal to 0 for all I and j. The sum of probabilities in each row must be equal to 1. This ensures that from any given state, the system must transition to the same state in the next step. The transition matrix is the DNA of the Markov chain. It encodes the complete dynamics of the system. All properties of the chain, including its long-term behavior, the classification of its states, and its predictive capacity, are derived directly from the mathematical properties of the matrix. Therefore, the central task in building a Markov model is the estimate and analysis of P. While today we are only going to focus on time homogeneous discrete time Markov chains with finite state spaces, it is useful to understand their place within the broader family of Markov processes. From the following visual, we can see that there are three distinct types of Markov processes. The first one is a discrete time Markov chain, which we just discussed, where both the time and state space are discrete. The second classification is a continuous time Markov chain, where we have a continuous time but a discrete state space. The third classification is a Markov process, which is the most general classification with a continuous time and continuous state space. So, if we compare DTMC and CTMC, DTMC models state changes at fixed time intervals, making them suitable for analyzing closing stock prices. CTMCs allow state changes to occur at any point in time, which is more realistic for phenomena like the arrival of trades or sudden interest rate changes. While the transition matrix P defines one step moments, we are often interested in the probabilities of transitioning between states over multiple steps. The n-step transition probability, denoted by Pijn, is the probability of moving from state I to j in exactly n steps, and Pijn is equal to P of xm plus n is equal to j, and P of xm is equals to I. These multi-step probabilities are governed by the Chapman-Kolmogorov equation. The fundamental equation states that to get from state I to state j in m plus k steps, the process must pass through some intermediate state z after m steps. By summing over all possible intermediate states, we get P of ij m plus k is equal to sigma of P of I z m and P of z j k, where z belongs to S. A remarkable and powerful consequence of this relationship is that when expressed in matrix form is that the n-step transition matrix Pn is simply the one-step transition matrix P raised to the power n. This result demonstrates the elegance of matrix representation, allowing for the efficient computation of long-term probabilities through matrix multiplication. Now let's look into the classification of its states. Understanding these classifications is crucial for interpreting the model stability and predictive power. First, we'll look into recurrent state. A state I is recurrent if, starting from I, the probability of eventually returning to I is 1. If this probability is less than 1, the state is transient. In financial terms, a stable market condition like low volatility growth might be modeled as a recurrent state, as the market is expected to return to it eventually. A sudden anomalous event like a flash crash might be a part of a sequence like a transient state, from which the market will never return. The next classification is an absorbing state. This state is a special type of recurrent state that once entered cannot be left. This means that the probability of staying in the state is 1. Absorbing states are essential for modeling terminal events. In credit risk modeling, default or bankruptcy is often an absorbing state for a company's credit rating. The next classification we'll look into is irreducibility and aperiodicity. A Markov chain is irreducible if it is possible to get from any state to any other state in finite number of steps. This means that the state space is not broken into discrete subsets. A state is aperiodic if return to the state can occur at irregular time intervals, rather than being forced into a fixed cycle. A chain where all states are aperiodic is itself aperiodic. A chain that is both irreducible and aperiodic is called ergodic. Ergodicity is a critical condition for the existence of a unique stable long-term equilibrium. For a ergodic Markov chain, one of the most important concepts is the stationary distribution denoted by the row vector pi. This is a probability distribution over the state space that remains invariant or unchanged after the Markov chain transitions. Mathematically, it is a probability vector pi that satisfies the equation pi p is equals to pi. This equation reveals a deep connection to linear algebra. The stationary distribution pi is normalized left eigenvector of the transition matrix P corresponding to an eigenvalue of 1. The existence of unique stationary distribution has a profound implication captured by the ergodic theorem of Markov chains. For any reducible aperiodic finite state Markov chain, the long-run distribution of states converges to the stationary distribution pi, regardless of the initial state. The value pi j can be interpreted as a long-run portion of the time that the chain will spend in state j. To apply the mathematical framework of Markov chains to finance, a conceptual bridge is needed to connect the abstract states of model to a tangible market. The most powerful and intuitive analogy is the concept of market regime. A market regime is a persistent period during which the statistical properties of asset return, such as the mean volatility and correlation, remain relatively stable. Financial markets do not behave uniformly over time. They cycle through distinct phases, like the bull market phase, characterized by rising prices and often low volatility, bear market phases, where the prices are falling with often high volatility regimes, periods of great uncertainty and large price swings, regardless of the direction, and the low volatility regimes, which are calm, stable periods with subdued price movements. These regimes can be viewed as the discrete states of the Markov chain. The tendency of these regimes to persist, a phenomenon known as volatility clustering, where high volatility days are often followed by more high volatility days, is naturally captured by a Markov model. Now, let us see a complete end-to-end implementation of a trading strategy built on a hidden Markov model. Here, the hidden Markov model treats market regimes as latent hidden states that must be inferred from the observable variables such as returns and volatility. This approach acknowledges the uncertainty in the regime classification and provides a probabilistic framework for regime detection and trading. So, the step one is data acquisition. We begin by downloading the historical data for the S&P 500 ETF, denoted by the ticker SPY, a widely used proxy for the US equity market. Two canonical features are extracted. The first one is the logarithmic returns, which is added as a new column to the dataset extract and is calculated as ln of price at time t by price at time t minus 1, ensuring time additivity and better statistical behavior than simple returns. Now we calculate volatility, a simple 30-day rolling standard deviation of log returns serving as a proxy for the recent market turbulence. So we add the volatility column into the dataset, which is a rolling, and at last, our load data function returns this new dataset with the log returns and the volatility. Now we define a new function known as the fit Markov model, which takes in the DF or the dataset and the states, which is by default equal to 2. Instead of directly clustering observed features into regimes, we fit a Gaussian hidden Markov model. Each hidden state is assumed to generate returns and volatilities following a multivariate Gaussian distribution. So first we extract X, which is this the sliced data frame containing only log returns and volatility. And we fit this to the Gaussian hidden Markov model we just discussed. We use two hidden states to capture the most fundamental market dichotomy, which is bullish versus bearish. The states are then interpreted by comparing their mean log returns. After fitting the Gaussian HSN, we use the train model to assign each observation in X to the most likely hidden state. So the hidden states is a vector like 0, 0, 1, 1, 0, 0, labeling the regimes. Here, we align the predictions with the data frame. Sometimes the model input X is shorter due to the dropping of NA values, which we did here. So we only take the last rows from the DF and we add a new column, regime, with the predicted states. Here, we group by regime and compute the average log returns in each regime and find which regime has the highest mean return, assuming that the regime with the highest return is the bullish regime. For example, if regime 1 has higher average returns, then that is a bullish one. Here, we relabel the regimes. This normalizes the regime labels to 1 is equals to bullish regime and 0 is equals to bearish regime. This way, regime interpretation is consistent across runs. And at last, we return the data frame with a new regime column, where each row is labeled as 0 or 1. After this, we define a class called the Markov regime strategy. So this class is a trading logic we are going to backtest today. It inherits from strategy, a base class provided by the backtesting framework. This tells the backtester how to trade based on the regime signals produced earlier. The first step, or the initialization step, runs once at the beginning. The self.i here is a helper that registers an indicator, which is a series of values aligned with the backtest data. Here, the indicator is just the regime column from the data. So self.regime will hold a time series of regime values. 0 is equals to bear and 1 is equals to bull. After this, we define the trading logic in a function called the next. Next is called on each new bar in the backtest. This is where the strategy decides whether to buy, hold, or sell. If the self.regime of -1 is equals to 1, that is, the most recent regime value we got says it is bullish, we enter a long position if you're not already in a position. Otherwise, if you're already in a position, we'll just hold. If the most recent regime value is not 1, that means it is equal to 0, stating the bearish one in our assumption. So in this case, we'll check if there is any position and we will close the position if there is any. Now we run the backtest. First, we'll load the data and send the data into fit Markov model to get the regime data, and we send it to the backtest function of the library backtesting, where we run a strategy using the backtesting framework with a starting capital of 100,000 and a commission of 0.001 or 0.1%. So on running this strategy, we got an output like this. The key results are the final return using the hidden Markov model strategy is 581.7%, whereas that of the buy and hold is 600.2%. The CAGR percentage of hidden Markov model is 9.31, whereas that of the buy and hold is 9.6. The Sharpe ratio of the hidden Markov strategy is 1.18, but for the buy and hold is 0.95. The Sortina ratio is 1.94. So the Sharpe ratio for the buy and hold is approximated from the web using the historical data. And we assume the Sortina ratio for the buy and hold also to be lower than that of the HHM strategy, which has a Sortina ratio of 1.94. And the maximum drawdown percentage of the HHM strategy is somewhere around minus 9.97%. Whereas the basic buy and hold can have higher drawdown in phases like this or this. And the number of trades taken in the hidden Markov strategy is 13. Whereas for the buy and hold, it is 1. And the win rate for all the trades of the hidden Markov model is 100%. So from this, we can interpret that hidden Markov-based regime strategy demonstrated comparable returns to the buy and hold, but with significantly lower drawdowns and excellent risk-adjusted performance, proved by a Sharpe of 1.18 and Sotino of 1.94, which exceed those typically achieved by passive SPY holding. And we took remarkably few trades of only 13, and each of them are highly profitable with 100% win rate. This indicates that the hidden Markov model's ability to stay invested only during the inferred bullish regimes helped avoid major drawdowns while still capturing most of the equity market's upside. So we can enhance this hidden Markov regime strategy by using more states or richer features and adaptive recalibration. In this example, we use a hidden Markov model-based regime trading model because it offers a statistically grounded alternative to observable state Markov chains. And my observable state Markov chain model is having some technical issues. So I cited my point of view into a HHM-based regime trading model. This model treats regimes as hidden, and it better reflects real-world uncertainty in market classification. While the returns are only slightly below buy and hold, the model achieves superior risk control and smooth equity growth, highlighting its practical value as a defensive strategy. This positions hidden Markov models as a powerful foundation for future research into adaptive, probability-driven trading systems.